Thank you, Mr. Chairman. Thank you for holding this hearing, and want to thank all the witnesses for their participation on this exciting subject. For Dr. Reitze and Dr. Shoemaker, because the expansion of the universe is accelerating, I'm told that the scientists theorize a mysterious dark force is pulling us apart, and that only 5% of the universe is visible to us. They say dark matter is 27%, and dark energy is 68% of the universe. That's just what I read. Can the gravitational waves help us understand the missing dark matter and the dark energy better?
Yeah. So let me start, and David can comment. It may be possible. First of all, gravitational waves themselves exist. They're ubiquitous, just like dark energy and dark matter, but they're a very, very tiny fraction. I mean, you can sort of add up how much energy density is in from gravitational waves, and it turns out to be very tiny. But it may be that gravitational waves interact with dark matter in a way that we haven't theorized yet or calculated. So it may very well be that somebody will come up with an idea to use LIGO or maybe LISA, the space-based detector, to detect them. So it is, it's one of those things where now that we've detected gravitational waves, people are going to start thinking about how can we use it to understand other more fundamental things. Dark energy is trickier. I once heard somebody say that dark energy overstates our energy or our knowledge of this phenomena by 2 words: dark and energy. We really don't even know what it. Yeah, there's getting better understanding of it, but it's still you can measure it, but to understand it is kind of hard.
Let me add that we're already one step along the way by having seen just how well our discovery, our first discovery, matches general relativity. It is astonishing how well Einstein's theory from 1916 matches what we saw, and that already excludes some possibilities for some things going haywire in our understanding of the universe. So that's already a set of constraints, and we think as we see each new source, we'll probably put new limits. Maybe we'll discover something which is different than we expect, and that would really be a key, or maybe we'll find that our theories are better and better confirmed. But either way, this new window on the universe gives us a possibility to close some opportunities that would otherwise not be there to zero in on what the real answer is.
If it took 100 years to go from Einstein's equations to discovering they're actually correct, just wildly thinking, what do you foresee in the next 100 years? And all of you just comment on that if you don't mind.
So my favorite philosopher is a gentleman named Yogi Berra.
Yeah.
And he said predictions are difficult, especially about the future. You can look back 100 years ago when general relativity was first postulated, when quantum mechanics were first postulated, and it was, at least it would have been impossible for me to project forward where we might be. That's the thing about science that's so great, that you never know where your big breakthrough is going to come from. So for example, everybody probably, or some people have been through MRI, getting diagnostic imaging from MRI. That comes from an obscure phenomena that was investigated in the 40s and 50s by nuclear physicists and condensed matter scientists. So I wish I could answer. If I could, I would probably make a lot of money in the stock market, but I just don't know.
We love wild speculation in this committee. and that's just what Einstein was 100 years ago, actually.
Let me say that I also don't have an imagination big enough to think what this will help in 50, 100 years from now. But I think there are surprises that are a lot closer. We are looking at the dark side of the universe. You talk about dark matter, dark energy. We are looking at the dark side, black holes, of which we know very, very little. These surprises are just around the corner. That's what I imagine the best side of this story is.
I want to emphasize how well chosen your time scale is, in that it can take 20, 50, or 100 years for these discoveries to come out of ideas that start to emerge now, and the consequences can play out over those time scales.
I don't have too much to add. I'm an instrument builder. I love the technologies. I know we'll be doing wonderful things with the technologies that we're developing 5 or 10 years from now. What will happen 100 years from now, I have absolutely no idea, but it will be neat.
And finally, Dr. Crim, I was wondering, as the field of gravitational wave astronomy moves forward, how are the NSF and NASA cooperating on supporting the field?
We have a very effective and close collaboration with NASA. The simple way to describe it is we do ground-based astronomy, they do space-based astronomy, but that means that oftentimes experiments we fund are very complementary to ones they fund. For example, we have a collaboration on their exoplanet program making ground-based radial velocity measurements to understand the mass of planets around other stars. So we have joint committees where we talk constantly, and the physics and astronomy that unites this effort is common to us both, and we're in really good contact.
Thank you. Thank you, Mr. Chairman.